Good morning, students. Next, in this second unit, we are going to discuss about small signal analysis of common base amplifier. Okay, here is the basic circuit diagram for the common base amplifier. Here, base is common between the input and output. Emitter is the input, collector is the output. Base is common between input and output. To provide biasing, we have to provide two separate DC sources. For the emitter, you have to provide minus VEE. For the collector, you have to provide plus VCC. Okay. So, this is the circuit. As per our analysis steps, first we have to draw the AC equivalent circuit for this one. When I am short circuiting the capacitors, we are getting that RS as it is. RE will be grounded because DC sources are grounded now. So, it is grounded. It will be connected to minus VEE. And then this RC will be parallel with RL. Okay. This RC will be parallel with RL, and then RB will be get cancelled because CB, when it is connected directly to the ground, it will be short circuited, so RB is not having any effect. And then when I am replacing this common base with the equivalent hybrid pi model, that will be like this one. Okay, that hybrid pi model equivalent circuit will be like this. We are having RS, RE, and then R pi, and then current will be flow from collector to emitter GMV pi, and then RC parallel with RL circuit will be there. Okay, RC parallel with RL, RLs we can write it separately, RC parallel with RL. Okay, this is the AC equivalent circuit. Next we have to go for analysis. When you are going for the analysis, here R0 is assumed to be infinite, so I am omitting the R0. Next we have to calculate the voltage gain. First we will calculate the voltage gain and current gain, because when you are calculating the input resistance, it's include both the input side and output side. Since the current connects both the input and output, the calculation will be somewhat tedious. So let me start with that voltage gain AI. Okay, looking at figure, V0 can be given as minus GMV pi into RC parallel with RL. Okay, when I am taking that output side, we are having a current GMV pi, but that is a flow in the opposite direction, so minus GMV pi. Then output resistance RC parallel with RL. Okay, then apply KCL to the emitter side. Emitter node, we are getting that one, Vs minus V pi divided by RS plus, when you see this one, when you are looking at the emitter side, we are having current that is Vs. Vs is 1 voltage and V pi is 1 voltage, and that will be given as Vs minus V pi. Both are in opposite side. Okay, Vs will be plus minus symbol will be there. See that one. Vs is plus minus Vs. If you see that one V pi, so only I give that in the blue color. Minus plus V pi. Okay, so we are writing that one. Vs minus V pi divided by Rs, that is the current flow through the node, and then V pi by Re plus V pi by R pi plus Gm V pi equal to 0. Okay, these are all the current, total current leaving the node. Okay, then if you are separating that one, Vs by Rs minus of minus plus V pi by Rs plus V pi by Re plus V pi by R pi plus Gm V pi equal to 0. Then I am taking that V pi commonly out. Vs by Rs plus V pi into 1 by Rs plus 1 by Re plus 1 by R pi plus Gm. Okay, this can be written as parallel combination of these things. Okay, then from that one, V pi can be given as taking that Vs Rs on the right hand side, we are having V pi into 1 by Rs plus 1 by Re plus 1 by R pi plus Gm can be written as 1 plus beta divided by R pi. Okay, that is equal to minus Vs by R pi. And then I am taking that V pi on the other side. Remaining things taking down, we are having that minus Vs by Rs into that parallel combination inversion. Rs parallel with Re parallel with R pi divided by 1 plus beta. And then our output voltage V0 can be given as Gm into, we have already obtained that one, minus Gm V pi. Instead of that V pi, I am substituting this V pi. So we are getting V0 in terms of Vs. Okay, in the voltage, in that equation V pi, we are having minus Vs by Rs na. So when I am substituting that one, the voltage gain V0 by Vs can be obtained. Okay, that is equal to AV equal to GM into RC parallel with RL divided by RS into the parallel combination of RS, RE, R pi by 1 plus beta. Among this one, RS is high value. Okay, va? So when RS tends to 0, here that RS tends to 0 means RS is not exactly equal to 0, it is very less value. So when you are taking parallel combination of these things, RS will be considered for that parallel combination. You know that when you are taking parallel resistance 1 by 1 mole, 1 ohm, 2 ohm or 3 ohm, when we are taking that parallel combination, the output equivalent resistance will be mostly equal to the lesser than the less value. Okay, so RS is less value, so it will be equivalent to RS. So when I am taking that RS as equivalent value for this one, that RS get cancelled, we are having AV equal to minus GM into RC parallel with RL combination. Okay, va? Sorry, AC equal to plus GM into RC parallel with RL, because on that minus will be get cancelled by minus VS by RS. Okay, so this is the voltage gain. Next we have to go for the collector gain. Okay, va? By applying KCL to the emitter node, we are getting that one II plus V pi by RE plus V pi by R pi plus GM V pi equal to 0. In that one I am taking V pi separately. So my V pi will be equal to minus II into RE parallel with R pi divided by 1 plus beta. Okay, already we have obtained that one. Then our I naught can be written as minus GM V pi into RC parallel with RC divided by RC plus RL, that is by current division rule. Okay, so instead of this V pi I am substituting this V pi, because our current gain is I naught by II. So by taking that II on the other side, I naught by II, that current gain can be given as minus of minus, it will be plus GM into RE parallel with R pi by 1 plus beta into RC by RL. Okay, this will be our current gain. When RL tends to 0, when RL tends to 0, what happened? When you are not bringing that one load effect, then we are having RC by RC equal to 1. So that equation, similarly RE parallel with R pi. In this also, it will be approximately equal to R pi. Since R pi value is smaller, that R pi it will be equal to R pi. So we are getting that one GM R pi divided by 1 plus beta. We know that one GM R pi is beta. So this can be written as beta divided by 1 plus beta. 1 plus beta is approximately equal to beta. So current gain is approximately equal to 1. We know that one alpha, that is the current gain of common base amplifier, is always nearly unit equal to 1. Okay, va? So that is proved here. Next we have to find the input resistance. To find the input resistance, this is our circuit for this input resistance. We have to obtain the input resistance here itself. First we have to find the Ri dash, then we have to go for the parallel combination of Re with the Rb with Ri. Okay, so when I am taking this equation, the output resistance Ri can be obtained by applying KCL to the input node. When I am applying KCL to the input node, we are having current that is GM V pi is leaving and IB is leaving, then RC parallel with RL combination also leaving. So we can write that one V pi by R pi plus GM V pi equal to V pi into 1 plus GM R pi divided by R pi. Okay, this one V pi by R pi is the current leaving. Okay, GM V pi is the current leaving and IA is the only current entering. Okay, so IA can be written as what we have written here, IA. Here we had the combination IA. So IA can be written as V pi divided by RE parallel with R pi plus 1 R pi divided by 1 plus beta, that is written here. Okay, va? So V pi by R pi plus GM V pi equal to V pi into 1 plus GM R pi divided by R pi. So in this one, when I am taking V pi as a common, we are getting that one V equal to, this will be equal to V pi divided by 1 plus beta by R pi. Okay, va? So our Ri dash can be given as V pi by II. So this can be given as V pi R pi divided by 1 plus beta, that is approximately that can be given as Re. Okay, Next, Ri can be given as Ri dash parallel with Re, that is approximately equal to Re only. Okay. Next, we have to find out the output resistance. When we are taking that, considering the output resistance, input source is short circuited, so Rs will be come in parallel with Re, and then R pi also parallel to that one. And when I am taking that one, when we are taking that output resistance, our current source will be open circuited. When we are open circuiting the current source, these Rs, Re, R pi is not come into effective to the output side. So the only thing come into effective at the output side is RC. So the output resistance R0 will be equal to RC. Okay, well, that's all about that common collector amplifier small signal analysis. We have obtained voltage gain, current gain, input resistance and output resistance. Okay, all.